All right, so it's our third lecture. Today I'm going to be introducing the basic ideas of Lagrangian mechanics. And Lagrangian mechanics is kind of the grown-up version of Newtonian physics. It accomplishes all the same things, but allows us to do a little more and understand the system a little bit better, especially mathematically. So the idea of Lagrangian mechanics comes from considering this quantity that we call the action, that we denote with S, and that I'll fill in the right side in a bit, but let me just explain the sort of physical setup. If we think about, let's say, like a one-dimensional system, then we could plot its position over time. So let's say this is position x, this is time t. And then if we know that over some time interval a to b, that we know with certainty where the particle is at time a and time b, so let's say here and here. That's it. The physical trajectory, the one that comes as a result of the laws of physics, is the one that will minimize this quantity, the action. Okay. So what exactly the action is then is that it's the integral over time from a to b of some function that we call the Lagrangian. And usually this will depend on the position of the particle, the velocity, which we denote as x dot. So I think you weren't here for the last one, but we're basically replacing time derivatives. So if you have the time derivative of something, then we call this like f dot. So two time derivatives, you put two dots, and that's a double dot. And you could do more from there. So, and on that, it could depend on higher order derivatives, but usually it won't. It can also depend explicitly on time. So not necessarily to the position, but just on time itself. All right, so we integrate that over time. Okay. And so really you should be thinking we're integrating this, and you don't need to worry so much about this. Okay. So in principle, we could have a lot of different trajectories if we just ignore physics. You know, we could have something that's just like a straight line. We could have something like this. We could have really crazy ones, like that. Ignore that I went back in time. And for every conceivable trajectory, we'll place sort of minimal constraints on what those trajectories could be. But for every conceivable trajectory, we could get a value for the action based on integrating this quantity. And the fundamental physical principle of Lagrangian mechanics is that the one that actually is the one that happens in real life is the one that gives the least action. So that's called the principle of least action. Okay, so in practice, this doesn't actually have to be the least action. What it really means is that action is sort of stationary at this trajectory. And what does stationary mean? Well, we can think about it in terms of just regular functions instead of this sort of construction. So if you consider two different functions, let's say some sort of parabola, like that, and then some sort of cubic function. So let's say like y equals x cubed, something like that. So the parabola actually has a minimum, right, around roughly here. And because it is a minimum, we know that at this point, the derivative of the function cannot be non-zero, right? It must be 0. Because if it were non-zero, then you would have that in a sufficiently small sort of neighborhood around that point. If the derivative were non-zero, then on one side the function is decreasing, which would contradict that it's a minimum. Okay, so the derivative at this point must be 0. But what the derivative being 0 really means conceptually is that if we vary our input like a very, very small amount, then the sort of induced change in the function is 0. So for functions that are differentiable, the induced change is proportional to the amount you vary it, right? And that proportionality constant is the derivative. So saying that the function is sort of stationary at this point is saying that if you sort of wiggle the input a little bit, the function doesn't actually move. And so the derivative is 0. Those two ideas are equivalent. And the same thing is happening here in y equals x cubed at x equals 0. The derivative is 0 at this point, but that doesn't necessarily mean that we have a minimum or maximum or anything like that. So just because the function is stationary doesn't mean that you've sort of extremized it in any way. Okay? So that's actually what happens with the action principle, is that we just need the action to be stationary, but everybody likes to call it the principle of least action. It's just a historical thing. Okay, so how do we actually think about the principle of least action? Well, let's say we do know what the physical trajectory is. Can't get in the line. Okay, so let's say it's something like that. So this is the one that we say gives the least action or whatever. Then the idea is that no matter in what way we kind of wiggle this trajectory, if that wiggling is sufficiently small, then the induced change in the action should be 0. So we're going to wiggle the trajectory over time in some way. That will produce a variation in the action, which will be infinitesimal. But in a more formal way, we can say this is 0. And that more formal way is probably something I'll do in videos by myself, because it requires a bit of formalism to think of. Okay, so this didn't have to be the case. This is kind of analogous to saying the derivative is 0. But as you know, usually the derivative is not 0. So if we had some different trajectory and wiggled it a little bit, it could produce some tiny little change or addition to the action. But for the physical trajectory, it won't. Right? So if we went like that a little bit, or like that a little bit, if it's sufficiently small, there's no change. Okay. Does that kind of make sense? So, no? Maybe? It's a bit weird, I know, but the idea is that in calculus, what you were doing with functions is that, let's say you're here. With limits and derivatives and stuff like that, you were thinking about what happens if I kind of wiggle the input in a sort of infinitesimal way. How does that change what the value of the function is? What is the behavior of the function under that? And you're doing the same thing here, except instead of your input being a number, your input is a function over this interval. So in some sort of way, we have an idea of varying a function in a small way. And then once we have that, we can start talking about what does it mean for this overall thing to have a induced response or induced change.
So basically you want to get the function into a position where any change in the function results in the smallest possible change in this arbitrary quantity, the action?
Not exactly. It's almost right. You want to get this function in the position where any sort of infinitesimal change in the function produces no change in the action. Right. Because if you're saying it produces the smallest amount of possible change, it still is not saying it's a minimum. So you could have functions like, to put it in sort of a function language, you could have functions like e to the x, where this has no minimum, right? Or if you say the derivative is also like bounded but non-zero, then you could have something like where this asymptote is kind of like linear. It goes like that. And then it still has no minimum. So what you want is for this infinitesimal change to be 0. All right?
That makes more sense now.
Is that good with you, Lily? Okay. Awesome. So this is the idea with one dimension, but in general we want to work with more than one dimension. So ideally we work in 3 spatial dimensions because that's real life. So, and not just that, we also want to work with systems with multiple particles, right? Not just one. So in general, we won't have the Lagrangian just depend on the position and that velocity, but also the different dimensions. We have like x, y, z. Then we could have each of those for each particle in there. So we get to this question about degrees of freedom of a system. So for one particle, so let's say capital N is the number of particles, and then we have the number of degrees of freedom. If we have one particle, then this particle can move in the x direction, the y direction, the z direction, and so it will have 3 degrees of freedom, right? And the idea is that if we know each of its trajectories along those dimensions over all of time, then based on that information, we could tell what its velocity is just by taking the derivative, right? So basically we're saying that we know x of t, y of t, and z of t for all of the times that we're interested in. Okay. So if we had 2 particles, how many degrees of freedom would we have?
By 2 particles, are you tracking the direction of movement of each individual particle, or the potential combinations of their movement?
You're tracking them simultaneously.
It's either going to be 6 or 9.
Okay. Can you make an argument for one of them or each of them? Or
if for it to be 6, if we were tracking one particle and the other particle independently, then we can make a case, well, there are 3 ways for particle 1 to move, and 3 ways for particle 2 to move, or 3 dimensions. So if you add them together, you get 6. Mm-hmm. But rather, if you track both of them simultaneously, you could say particle 1 can be moving up and particle 2 can be moving up, or particle 1 can be moving up and 1 can be moving along the y direction, and so you can create that list of 9 possibilities.
Okay. Yeah. So, do we care? How do I explain this? Do we care about the particular sort of combinations? So, I'm kind of looking for knowing at all times what is the x coordinate of the first particle, what is the y coordinate of the first particle, what is the z coordinate of the first particle, and what is the same for the second particle. So basically, I'm interested in knowing the positions of each particle at all times.
Sure.
In that case, does it matter sort of what combinations
Not
the
really.
two. Right. Yeah. So we actually would just have 6. Okay. So me introducing some random jargon that you don't care about. What you're talking about is the difference between a Cartesian product and a tensor product. And the second part is actually very useful, especially in relativity. But for this, we don't need that. We just need to know each piece of information. Okay, so this has 6. Okay, if I have 3 particles. Yeah, okay. If I had just, in general, n particles. N times 3, yeah. Or 3n. Okay. So, for n particles, we'll always have 3n degrees of freedom. And I want to talk about this because in some cases you don't want to use Cartesian coordinates necessarily. So there are some systems where it's much simpler to use a different coordinate system. So for example, you could use polar coordinates or spherical coordinates. So for example, if you have you have like a planet and then you have like a satellite in the gravitational field, the gravitational field will have this spherical symmetry, right? So in that case, it's a lot more convenient to use the radius from the center of this planet and then use the other angles, the theta and phi, from the spherical coordinates. And that will be a lot simpler than using x, y, and z. The point is, maybe I should just leave this up. The point is that going from x, y, z to r, theta, phi, you have the same number of degrees of freedom. Right? There are 3 things that we keep track of here, and 3 things that we keep track of here. So any sort of change of variables that we make in our coordinates must maintain the number of degrees of freedom. All right. So this is not the only kind of transformation that we're interested in. We don't know what transformations of coordinates will be useful, so we want to express our theory in a way that's okay with any kind of coordinates. So often we'll replace this by q and with an index I. And so this I runs over pretty much every degree of freedom, so that if you have n particles and 3n degrees of freedom, there will be 3n of these QIs. Okay? So in a normal situation, these QIs could be just x, y, z, or they could be r, theta, phi, or they could be something more complicated, potentially. So to make our stuff more general, we will express our Lagrangian as a function of these Q's. So it could depend on this sort of what we call a generalized position, and then a generalized velocity. I'll actually just leave out the t's because it's just clutter. Could depend on time, and then we integrate. So yeah, these things we call generalized coordinates, the q's. And from here, we're in a much better position to actually use this for physics. Okay. So let me go here. So the principle of least action through some kind of complicated math that you can also do in a non-complicated way that involves the multivariable chain rule, which I'm not going to do for the interest of time. It gives you, so least action tells you that what must be true for the physical trajectory of these QIs is that the partial derivative of the Lagrangian with respect to each QI is equal to the time derivative of the partial derivative of the Lagrangian with respect to the corresponding velocity. Okay, so this doesn't seem very obvious, right? How to get from this to that. Okay, so that's what I'm going to make a video about, because it's not obvious. This is not one of my trick questions this time. It's like, right. But the basic idea is that, okay, so for one, we went from this whole like integral thing and variations to a differential equation, right? And so you haven't learned differential equations, like the full theory or anything like that yet. But one basic thing is that, where do I have this? Oh, good, I erased it. Is that with this differential equation, we need some conditions so that we can actually solve it. So this is the idea of like, with a harmonic oscillator, you need the initial position and initial velocity to determine what the trajectory is. So what we had actually was that we knew all of these, the initial and final positions. So these were given. And that's what I said at the beginning, that we're minimizing the action, but we know the two sort of endpoints of the trajectory. And the theory of differential equations tells us is that we can use this, but equivalently, we can use the initial position and the initial velocity instead. Okay, and for simplicity, I'm going to use 0 as the initial time. So if we know what the Lagrangian is, the idea is that we can then solve this differential equation given these initial conditions, and that gives us the whole trajectory of the system, so all the particles involved. Okay, we don't know what the Lagrangian is though, and that's a problem. But the thing is that this sort of idea isn't just for physics. You can use it in a lot of applications in math. So how do we actually get this to correspond to physics? Well, the idea is that we're not trying to produce Newtonian physics out of this. There's a big misconception when people teach Lagrangian mechanics, like even in colleges, that we're somehow going to derive Newtonian physics from this. And that's not true. This isn't really a theory so much as it is a tool. And so the idea is that we have a differential equation. Newtonian physics also gives us a differential equation. It says that F equals ma. This a, the acceleration is the second derivative of the position. So this is a differential equation. Then if we can match this with this, so that if this is true, then this is true, you can actually go the other direction. And say if this is true, then this is true. And so the whole point is that our whole idea with the principle of least action is that it is exactly equivalent to Newtonian physics. All right, so our goal then is to find a Lagrangian so that this equation is the same as Newton's second law. Okay? Does that make sense? Okay, so now we need to actually do that. All right. So if we have a conservative system, can one of you tell me what the form of the force is, like in a particular direction? There's a sort of relation between the force and the potential energy.
Oh, the force is in opposite direction of the potential?
Right, but mathematically, like we have an equation.
The potential is the negative integral of the force with respect to position?
Yeah. And so what we want to do is basically invert that so that we can relate it to the differential equation. So if the...
So that would just be the derivative of potential with respect, or the negative derivative of potential with respect to position is force.
Yeah. So for the sort of ith, like the direction of the ith generalized coordinate, this is basically what we're saying. Or let's say we're working in Cartesian coordinates. So for a certain particle in a certain direction, the force is the negative derivative of the potential energy with respect to that position. Okay? So you guys learned that as like minus dv by dx, but this is just the generalization of that into more dimensions and then more particles. Okay. So what this equation, Newton's second law, is saying then is that in Cartesian coordinates, we would have this. So this mass could potentially depend on which particle it is, but that's not the important point here. Okay, let me actually write this the other way around. Is that okay? Okay, so we want to match this with this. Does anything kind of jump out?
At first, just looking at the left side of the equation, the Lagrangian coordinates to the negative potential.
Okay.
However, that's completely ignoring the right side of both of them.
Yeah. So it's a good start, right? We might want to say that these two are equal. And so you might want to say the Lagrangian is the negative potential energy, but then if you differentiate, so if you differentiate this with respect to the velocity, you get 0, which is potentially an issue. So you don't necessarily want this, but maybe what you want is this plus some sort of function of the velocity. Okay? So,
And
yeah.
that would just be the acceleration function with respect to time, right?
What do you mean with respect to time?
Never mind, keep going.
Yeah, you're on the right track. So let's keep that in mind. So we match the left sides. Let's try to match the right sides. So what's the first thing going on here? Or maybe the last thing is a better thing to ask.
Taking the derivative with respect to time.
Yeah. So it would be nice if this was the time derivative of something.
Which it is of the velocity function.
Yeah. But what about the m?
What?
But the mass?
Well, the mass is constant, so
Right.
I guess it's the derivative of the momentum function.
Yeah. I'm going to call it this because we're going to see some stuff with momentum later, and it's going to potentially be weird in a few days. But this is the time derivative of this, the mq dot. So what we might want to say is that this partial derivative, so dl by dq dot, is equal to mq dot for each I. Okay. Now, is this the derivative of something that's a function of q dot? So instead of thinking about sort of the independent variable being q, you want to think about it being q dot. So what do you need to take the derivative of to get something that's a linear function? Sorry? Quadratic? Yeah, exactly. So you could think of integrating this with respect to q dot. And yeah, so this is the derivative of this. Okay, this is the velocity. Does this remind you of something?
Kinetic energy.
Yeah, exactly. So if we say the Lagrangian is, so we might want to match this with this then, in part. Okay, so we would be summing over each I for this because we need each of these to be true. So we'd have the kinetic energy in one direction plus the kinetic energy in another direction plus the kinetic energy in the z direction, and then that for every particle. And then once you take each of these derivatives, you would get this. Okay? So let me just write it in to make it less confusing. So I'm summing over all the I, and that would be from 1 to 3n. Okay. And then I could have the position dependence in the Lagrangian be from the potential energy. So this is going to be outside the sum, but I want to subtract the potential energy, which could depend on all of these generalized coordinates, right? So this I'm just saying it would be like q1, q2, q3, all the way up to that. Okay, so what is this actually? It's the kinetic energy minus the potential energy.
And just to confirm, this is a conservative potential?
Yeah.
Okay.
So this is when we're dealing with a conservative system. When we're not dealing with a conservative system, it's more complicated, but I don't want to get into that because it's not conceptually helpful. Like, it's not important for the main ideas of Lagrangian mechanics. Okay. So that's the big idea. So when you start off learning Lagrangian mechanics and you talk about basic systems in classical physics, you want to look at what is the potential energy of the system, what did I just say? Yeah. What is the kinetic energy of the system? What is the potential energy of the system? So then what is the Lagrangian? And then using the Euler-Lagrange equations, how do I get the equations of motion, which would basically correspond to Newton's laws? Okay. So let me go to an example just to make this a bit more concrete. See, this is somebody else's stuff, so I feel like I don't want to mess with that. No, I'll just use this. Okay. So let's do some pretty simple examples. So let's say we have a free particle. So what that means is that, for one, we're going to do one particle. And for the other, we're not going to have any forces, so no potential energies. Okay. So if there are no potential energies, Lagrangian is equal to k minus v. So then what is the Lagrangian?
For a particle moving on a potential-less surface? Or
Yeah, except we're going to say it's a particle moving in 3D space. So it's going like, whatever.
sure. So the Lagrangian would just be 1/2 m q dot squared.
Yeah. And what are our q's in this case? Or what could we choose them to be? All right.
It could be x, y, or z.
Yeah. So our kinetic energies would then be, and we could factor this out. So the particle has some mass, and then we have x dot squared plus y dot squared plus z dot squared. And then no potential energy. Okay. So this is like one of the simplest examples you could have. The only way to make it simpler is just to cut down the dimensions. And so now we want to do this. So think about it for a bit, maybe like 30 seconds, and then tell me what you get. Or if it takes you less time, that's fine. I'll just sit and think about what I want to do next. And if you know, just feel free to blurt it out.
So I just got 0 equals m x plus y plus z, all in parentheses.
Like this?
I believe so, yes.
Okay.
With respect to each dimension, or if you just isolated it, it would be 0 equals mx, 0 equals my, 0 equals mz.
Yeah, so that's closer. Because remember, we have one equation for each degree of freedom. So this is true for each I. So we should have 3 equations. Okay. So a good thing to do whenever you get an answer is to check it through some sort of sanity check. So if we have a particle with no potential energy, it can still move, right? It would move in a straight line. That's what Newton's first law is. This is saying that x equals 0, y equals 0, and z equals 0, which means it just stays still at the origin. So that's probably not right.
Okay.
So let's go through the process of getting these equations.
I'm just not familiar with taking derivatives with respect to the dot notation.
Yeah, it's a bit weird, but it's actually, completely the same as everything you've done in multivariable. So you just have to think about this as being, like, without the square, it's the independent variable. So if it helps, like, replace it with u or something. So you'd be doing d by du of u squared, which is?
Just 2u.
Yeah. So if we do, let's say, the right-hand side for the x equation, so a good way to start is, I prefer to start with the left-hand side, actually, and then do this derivative and then take the time derivative. So does the Lagrangian depend on any of the position coordinates? No. That's what we made sure of when we said there's no potential energy. So the left-hand side will be 0. The right-hand side for the x equation will be this. we're differentiating this with respect to x dot. So we can ignore the other parts and just say we're doing the derivative of this, or not qx.
That would just be the derivative with respect to time of mx dot.
Yeah, exactly.
Oh, never mind. Okay.
Does it make sense now?
Yep, I just did a stupid calculus mistake and went backwards instead of
It's okay. But you can see what this is going to be, right? So what would this be?
Would just be
So you're taking the time derivative of x dot, right? So you got the m, and then you're doing this. I know this notation's a bit, so I'll just write it out.
So it's the second derivative of x with respect to time, right?
Yeah. So
it would just be acceleration? Or
exactly.
Since it's the second derivative, there would be two dots over the x?
Yeah. So both, yeah. So you could say this is, if you're doing a sort of AP physics kind of thing, you might write it like this, as this, like a sub x or something like that. But yeah, we would say this is x double dot. So that's the second derivative of x with respect to time. Okay? So it's just the same as this, right? But there's no potential energy, so this side is 0. Okay? So I could have just directed you to this, but I want to make sure that you're comfortable with the idea of going through this process. Okay. Is the x part of the Lagrangian especially different from the y or z parts? No. So we have our first equation, which is this. Our second, or y equation, will be this. Our z equation will be this. What physically is this saying?
There's no net force in any direction.
Yeah, there's no net force on the particle, so there's no acceleration on the particle. So this is the kind of Lagrangian way of saying that if you have no forces, because all our forces are coming from potential energies, if you have no forces, that means you have no acceleration. And this is the equivalent of Newton's first law. Okay? All right. How do you feel about this? Okay.
It's starting to make more sense, but the most unfamiliar part of it is the dot notation.
Yeah.
But that's going to take some getting used to.
It's just because this takes up so much space. And also, I mentioned it last time, but the dot is what Newton used.
Yeah.
So people just kind of went with it. Okay. So, some things to notice. Yeah? Oh, okay. So, each of these are the time derivatives of the mass times the velocity in that direction, right? So what are each of these in the, what you're familiar with?
Momentum.
Exactly. So we have 0 is equal to the time derivative of the momentum in that direction. So if you have the derivative of something equals 0 for all time, what does that mean about that thing?
Constant.
Exactly. So if each of these are constant over the whole time, what this is saying is that the momentum is conserved. additionally, the right-hand side of each of these is the time derivative of this thing, right? So whenever you have a situation like this, 0 equals d by dt of this thing, so it could be coming from this. And so we get this sort of correspondence between this derivative and what we call, or what is the momentum in that.
Bye, thank you.
It's okay. Bye. Right. So when we're just dealing with Cartesian stuff, this is pretty obvious, right? This derivative will always be our familiar idea of momentum because we're coming at it from this form of the kinetic energy. So we kind of make this this idea general in saying that if we have these generalized coordinates with the q's, then we define these pi's to be the derivative of the Lagrangian with respect to qi dot. Okay, so these are called conjugate momenta. Or I guess the singular would be conjugate momentum. And the idea in which they're conjugate is that they're conjugate to that generalized coordinate. So conjugate momentum for Cartesian coordinates are just the ordinary, p equals mv. But if you did stuff in spherical coordinates instead, then that's not necessarily the case. So you'd have some sort of radial momentum and then different angular momentum, which is a familiar word, right? And those often actually are angular momentum. So I don't have too much time. So let me just say a few more things. Okay. So this was 0, why?
Because there was no potential, or there were no forces acting on the object.
Yeah. And so specifically, because of that, there was no positional dependence in the Lagrangian. So on a case-by-case basis, if we look at a specific degree of freedom, and the Lagrangian does not depend on that generalized coordinate, then this is always 0, right? The conservation of momentum came from this being 0, right? So if we have that, the Lagrangian does not depend on a specific generalized coordinate, then this conjugate momentum is conserved. Does that make sense?
Yeah.
Okay. So the equation of motion that we get is this. Which is just, or we can just write as pi dot. So pi dot equals 0. Okay. When this happens for a qi, we say that this qi is a cyclic coordinate. I don't know why, but that is what it's called. Oh well. Yeah. So if you have cyclic coordinates, it's very convenient because then you automatically know that the corresponding momentum is conserved. And so it's actually a really nice way to just get rid of degrees of freedom. Okay, I started late, so I'm going to take like a bit more time.
Yeah.
And we can actually see this in a specific example. Do you think it's okay if I erase this?
Definitely the right side. I don't know about the left.
Yeah. I'll just do that.
Yep, that's
Okay.
the screen.
So let's say we're talking about throwing up a ball or something like that.
Mhm.
We're going to treat the ball as a point. Okay. So let's say we set up some sort of coordinate system so that, gravity is going downward. And then we're throwing up a ball, say from here, in some direction. Okay. Say this is x, this is y. What is the Lagrangian of the system?
It would be, with respect to the x direction, 1/2 mx squared.
X squared?
X dot squared, sorry.
Yeah.
1/2
That's okay.
mx dot squared minus mgy. So I guess you need to include with respect to x, it's just that, but with respect to y, it's 1/2 my dot squared minus mgy.
So remember, the Lagrangian is a scalar,
Mhm.
so it's going to include everything, right? It doesn't have it's not like a vector where you have different quantities that correspond to different directions. So the total kinetic energy is 1/2 mx dot squared, and then plus 1/2 my dot squared. And then the potential energy is mgy. Okay? All right, then let's do this. Okay. So, do you want to start with x or y?
Well, x seems to be easier.
Yeah. So, for the x equation, what should we start with?
dl by dx is 0.
All right. So, let me write this here. Awesome.
And then dl by dx dot is mx dot, and then by dt, that would be just mx double dot.
Exactly. Okay, so what we get then is that 0 equals mx double dot. And what does this tell us?
There's no force acting in the x direction.
Mm-hmm. So then what could we say about the momentum?
It's conserved.
Yeah, the momentum in the x direction is conserved. And how could we have identified that immediately? Well, this x is a cyclic coordinate because there's no dependency on x in the Lagrangian.
Sure.
Okay, and then the y equation?
So dl by dy is negative mg. And
Okay.
then dl by dy dot is 1/2, or it's just my dot, and then by dt, that's my double dot.
Right.
So
So,
there's a second dot on the y, I believe.
yeah, I just haven't done the time.
Oh, okay, yeah.
So then, yeah, we would get this. So our Euler Lagrange equation is minus mg equals my double dot. Okay, so what is this saying?
Y is dependent, or the force of y is dependent on position, and that is proportional to negative mg.
Well, is it dependent on the position?
Or the potential, I should say. not
Right.
The force.
And what about the force?
The force is constant.
Right. And yeah, so the force in the y direction is minus mg. And so the minus means what?
It's pointed in the negative y direction.
Exactly. So our force would be like this. That's a G for people watching the video. Awesome. So from the Lagrangian, then, you get these equations that you would have from Newtonian physics. So that's good. Now, why is it useful? Because, you know, a bit ago, you might have been looking at this and asking the question, if we're just going to match this with Newton's second law, then what's the point? Why don't we just use Newton's laws? The answer is, well, we've seen one example in which it becomes really easy to identify conserved quantities in this Lagrangian framework. If the Lagrangian doesn't depend on a specific coordinate, then this conjugate momentum is automatically conserved. And that's not the only benefit. There are other ways in which you can get conserved quantities. So it's not just through this sort of cyclic coordinate business. And that's probably going to be the discussion of tomorrow when we talk about Neuters' theorem. And the other thing, well, there are actually lots of things. So for one, it becomes a lot easier to work with energies instead of forces. Forces, they can point in a lot of directions. There can be a lot of complicated, sort of intermediary forces between different particles and stuff like that. But they can be really easily summarized in terms of just energies. And usually the potential energy is what makes it very simple. Another thing is that this generalizes very easily to more dimensions and more particles. We still just are talking about one function. And not just that, we can use this formalism of an action principle and then Lagrangian when we talk about fields, where for sort of trajectories, you just have these functions that depend on time. But fields depend on space and time. So we can sort of rework our Lagrangian and or the Lagrange equations to accommodate a Lagrangian that depends on all the spatial variables in time, and that because we're talking about fields. And then we get these equations of motion for fields and stuff like that. Maybe we'll have time for that later this week, but I don't know. But the point is that this action principle is very powerful because through this minimization and the Euler-Lagrange equations, we can get it to correspond to basically whatever kind of physics we're talking about. Okay? Yeah, that's probably all we have time for today. I don't know. Would you be willing to stay for like another 5 minutes?
Yeah, I have
Okay.
time.
I want to do just one more example. Okay. So my last example I want to talk about is a simple harmonic oscillator. It's really like an idealized, I guess simple harmonic oscillator is already idealized, but you could imagine something like an ideal spring. So let's say we have a mass on a spring. So you have a spring. You have a block of mass m. Let's say it's at equilibrium, which in this case is the natural length. And we're going to call the equilibrium position 0. So you could think of x as being the stretch or compression length. Okay. So this spring has a spring constant k. What then is the Lagrangian of the system?
The k would be 1/2 x squared, assuming that is it free to fall?
No, we're going to say that it's constrained to move in the x direction.
So it would be 1/2 mx dot squared.
Yeah. potential energy? Yeah, go ahead.
And then it would be plus, wouldn't it? 1/2 kx squared.
So let's check the sign. Because that often leads to confusion.
Mm-hmm.
So this is saying that the potential energy is minus 1/2 kx squared, right? So if we, let's say, stretch the block a bit, which direction is the force in?
It's to the left or in the negative x direction.
Right. So the force would be going this direction. And the force points in the direction in which the potential energy decreases, right?
Mm-hmm.
Yeah. So if the potential energy looks like this, and we push the block in this direction, then the force will continue pushing in this direction, right? Which is not what happens. So should we have the other way?
Yeah, it should be flipped.
Yeah.
Yeah. Across the x-axis.
Yeah. So the potential energy should look like this. So which means that it should be positive 1/2 kx squared. So in this case, this would be a minus,
Oh.
because we're subtracting the potential energy.
Mm-hmm.
Okay. Awesome. That's pretty much it with the Lagrangian, right? So now we can do our whole shtick with this.
Mm-hmm.
So what do we get?
So dl by dx is 1/2 k. Or sorry, that's
Okay.
not true at all. It is negative kx.
Yeah, exactly.
And then dl by dx dot is mx dot. So then d by dt is just mx double dot.
Exactly. So you can kind of see that, this whole thing, it happens a lot,
Mm-hmm.
right? As long as we have kinetic energy that looks like this, we'll get this. So the Euler-Lagrange equation says that, it doesn't matter which order I do it. It gives you this. And this should be pretty familiar?
Yep.
Yeah. So this is Hooke's law, or just the sort of spring force law. And so, if you've done a class in differential equations, you probably learned how to solve the specific one. You can express x in terms of sines and cosines. But I really just want to place importance on this differential equation because it's something that pops up a lot, even in systems that you don't expect. And another thing is that if you have the insight of expressing this stuff with sines and cosines, and you get these ideas with frequencies and periods, is that you can define this quantity omega, whose square is k over m. Okay?
And
So,
what is omega?
so omega will turn out to be the angular frequency
Okay.
of the oscillation. But for now, if we don't know the solution, we're just saying it's some number that we can make. Okay. So we can rewrite the Lagrangian as this. Or sorry, no. 1/2 m omega squared. X squared. Because m times omega squared is k. Okay, and this is the form that people prefer to put this stuff into. And then the equation of motion, well, we can divide by m, and what we get is this. Or you can write it as the sum of the two equals 0. Okay? Yeah. So, you can come up with really arbitrarily complicated examples, figure out the Lagrangian, figure out the equations of motion, as, like I said, fun or maybe not so fun exercise. And yeah, it just gives you the power to look at, pretty complicated systems, maybe ones that you didn't quite know how to handle with Newtonian laws, and now actually sort of solve them, basically get the equation of motion, right? The differential equation that tells you what the trajectory of the system is. Okay? And in math, we have a theorem that says that if we know the initial conditions, then usually there is a solution, even if we're not smart enough to find one. Okay, so I think that's it for the examples. And then tomorrow we'll be talking about symmetries and Neuters' theorem. So this is kind of where stuff we talked about with symmetries before pays off in terms of the physics and doing stuff with Lagrangians. Okay? Awesome.
All right.
So I'll hopefully see you tomorrow.
Sure.